Section: Introduction. We're going to talk about large language models, LLMs, and how they can be expanded into the realm of multimodal data, which includes both text and images. This expansion leads to the creation of large multimodal models, LMMs. However, creating these LMMs is not without its challenges. One of the main issues is the disparity between the amount and quality of multimodal data compared to text-only data. For instance, let's look at the LLAVA model. This model is built from a pre-trained vision encoder and a language model that has been fine-tuned with specific instructions. It's trained on only 150,000 synthetic image-based dialogues. This might sound like a lot, but when you compare it to text-only models like FLAN, which uses over 100 million examples across 1,800 tasks, it's quite small. This lack of data can cause a misalignment between the vision and language modalities. As a result, LMMs might produce outputs that are not accurately tied to the context provided by images. To address these challenges, we're introducing LLAVA RLHF, a vision language model designed for better multimodal alignment. One of our main contributions is the use of reinforcement learning from human feedback, RLHF, a method that has been successful for text-based AI agents. We're adapting it for multimodal alignment in LMMs. We collect human preferences, focusing on identifying hallucinations, and use these preferences to fine-tune the LMMs through reinforcement learning. This method can improve multimodal alignment at a relatively low cost. For example, we can collect 10,000 human preferences for image-based conversations for just 3,000. However, there's a potential issue with RLHF known as reward hacking. This is when high scores from the reward model don't necessarily lead to improvements in human judgments. To prevent this, we propose a more data-efficient alternative. We aim to make the reward model capable of using existing human annotated data and knowledge in larger language models. We do this by improving the reward model's general capabilities using a better vision encoder and a larger language model. We also introduce a new algorithm called Factually Augmented RLHF, FACT-RLHF, which adjusts the reward signals by adding additional information like image captions or ground truth multi-choice options. To further improve the capabilities of LMMs, we augment the synthetic vision instruction tuning data with existing high-quality human-annotated multimodal data in conversation format. We convert VQAV2 and AOKVK into a multi-round question and answer task, and Flickr 30K into a spotting captioning task. We then train the LLAVA SFT+ models based on this new mixture of data. Finally, we focus on assessing the multimodal alignment of LMMs in real-world scenarios, with a particular emphasis on penalizing any hallucinations. We create a set of varied benchmark questions that cover the 12 main object categories in COCO and include 8 different task types. This leads to the creation of MMHAL bench. Our evaluation shows that this benchmark dataset aligns well with human evaluations, especially when scores are adjusted for anti-hallucinations. In our experimental evaluation, LLAVA RLHF, the first LMM trained with RLHF, shows impressive results. We see a significant improvement on LLAVA bench, achieving 94%, a 60% improvement in MMHAL bench, and new performance benchmarks for LLAVA with a 52.4% score on bench and an 82.7% F1 on POPE. We have made our code, model, and data publicly available. Now, let's talk about the method. We use RLHF to align LMMs. A vision encoder and a pre-trained LLM are jointly fine-tuned on an instruction following demonstration dataset to produce a supervised fine-tuned SFT model. In the next stage, a reward model, also known as a preference model, is trained to give a higher score to the better response. The training data for pairwise comparison are typically annotated by human annotators. The aggregated preference data can be represented as a set of elements, where each element includes an image, a prompt, 2 associated responses, and the index of the preferred response. Section summary. Large language models, LLMs, can be extended to the multimodal realm by pre-training them with image-text pairs or fine-tuning them with specialized vision instruction tuning datasets. However, the scarcity of high-quality visual instruction tuning data can lead to misalignment between the vision and language modalities, resulting in hallucinated outputs. To address this, we introduce LLAVA RLHF, a vision language model trained for improved multimodal alignment using reinforcement learning from human feedback, RLHF. We propose a data-efficient approach that leverages existing human annotated data and knowledge in larger language models to prevent reward hacking and enhance the general capabilities of LMMs. Section: Reinforcement Learning. In this section, we'll discuss reinforcement learning, the importance of high-quality instruction tuning, the collection of human preferences, and the concept of factually augmented RLHF. We start with reinforcement learning, where a policy model is trained to generate suitable responses to user queries. This model is initially set up through a process called multimodal supervised fine-tuning. It learns by maximizing the reward signal given by the reward model. However, to avoid over-optimization issues, such as reward hacking, we sometimes apply a penalty for each token, which is derived from the initial policy model. This penalty is controlled by a hyperparameter, beta. Next, we discuss the importance of high-quality instruction tuning. Recent studies have shown that this is crucial for aligning large language models, LLMs. This becomes even more important for LMMs, as they navigate vast textual and visual domains. Clear tuning instructions are vital to ensure that the models produce outputs that are relevant to the context, effectively bridging the gap between language and visuals. For instance, LLAVA created 150K visual instruction data using the text-only GPT-4. However, despite careful filtering, the pipeline can sometimes generate visually misaligned instruction data. To address this, we propose enhancing LLAVA with high-quality instruction tuning data derived from existing human annotations. We then move on to the collection of human preferences. Inspired by recent studies, we differentiate between responses that are less helpful and those that are inconsistent with the images. To do this, we provide crowdworkers with a template to guide their annotations when comparing two given responses. Our goal is to prompt crowdworkers to identify potential hallucinations in the model's responses. Finally, we introduce the concept of factually augmented RLHF. We conduct multimodal RLHF on a subset of LLAVA conversations, with additional multi-choice questions and yes/no questions. However, we only use the first question in each conversation for RL training to avoid pre-existing hallucinations in the conversational context. We observed that the reward model is sometimes weak and cannot effectively detect hallucinations in the RL model's responses. To enhance the capability of the reward model, we propose factually augmented RLHF, where the reward model has access to additional ground truth information such as image captions to calibrate its judgment. This prevents the reward model from being tricked by the policy model when the policy model generates hallucinations that are clearly not grounded by the image captions. For general questions with COCO images, we use the 5 COCO captions as the additional factual information, while for AOKVK questions, we use the annotated rationals as the factual information. The factually augmented reward model is trained on the same binary preference data as the original reward model, except that the factual information is provided both during the model fine-tuning and inference. Section Summary. In this section, the authors propose a reinforcement learning approach for generating appropriate responses to user queries. They address challenges such as reward hacking by applying a per-token KL penalty and augmenting the training data with high-quality instruction tuning data. They also introduce factually augmented RLHF, FACT-RLHF, where the reward model is provided with additional ground truth information, such as image captions, to improve its judgment and prevent reward hacking. Section: Symbolic Rewards, Correctness Penalty and Length Penalty. In our research, we've noticed that some of the data we use in reinforcement learning, RL, comes with preset correct answers. This is true for binary choices like yes, no, in VQAV2 and multiple choice options like ABCD in AOKVK. We can think of these correct answers as extra factual information. So, in our FACT-RLHF algorithm, we've added a symbolic reward system that punishes choices that don't match these correct answers. We've also noticed that models trained with RLHF often give longer answers. While these detailed answers might be preferred by users or automated language model-based evaluation systems, they can lead to more hallucinations for language and multimodal models, LMMs. To address this, we've added a penalty based on the length of the response, measured in the number of tokens. Our base model uses the same network architecture as LLAVA. We use Vicuña for our language model and the pre-trained clip visual encoder, VIT-L14, for image features. We use a linear layer to convert image features to word embeddings. We use pre-trained checkpoints from LLAVA for the linear projection matrix, focusing on fine-tuning for multimodal alignment. For our RL models, we use the same architecture as the base LLAVA model for the reward model, but we project the last token's embedding output to a scalar value to indicate the reward for the entire response. We use proximal policy optimization with a KL penalty for RL training. To evaluate hallucination in LMM responses, we've created a new benchmark called MMHAL bench. Unlike previous benchmarks that evaluate response quality in a general sense, we focus on whether there's hallucination in the LMM responses. We've designed 96 image question pairs in 8 question categories and 12 object topics. We've noticed that LMMs often make false claims about image contents when answering certain types of questions, so we've designed our questions accordingly. When evaluating LMMs on MMHAL bench, we use the powerful GPT-4 model to analyze and rate the responses. Since the publicly available GPT-4 API only supports text input, we provide category names of the image content and a standard human-generated answer in the prompt, in addition to the question and LMM response pair. This way, GPT-4 can determine whether hallucination exists in the LMM response by comparing it against the image content and the thorough human-generated answer. Section Summary. In the RLHF algorithm, we introduce a symbolic reward mechanism that penalizes selections that diverge from predetermined ground truth options in RL data. Additionally, we incorporate response length as an auxiliary penalizing factor to address the issue of verbose outputs in RLHF trained models. We also create a benchmark called MMHAL bench to evaluate the hallucination in LMM responses, focusing on determining whether hallucination exists in practical user LMM interactions by using general, realistic, and open-ended questions. Section Results. In our study, we used LLAVA bench and our MMHAL bench as primary evaluation tools due to their strong correlation with human preferences. We also conducted tests on widely acknowledged large multimodal model benchmarks. We utilized MMBench, a multimodal benchmark that provides an objective evaluation framework consisting of 2,974 multiple-choice questions across 20 ability dimensions. This benchmark uses ChatGPT to compare model predictions with the correct choices, ensuring a fair evaluation of VLMs across different instruction following abilities. We also used POPE, a polling-based query method, to evaluate the object perception tendencies of large multimodal models. High-quality SFT data is essential for capability benchmarks. Looking at the specific performances for the capability benchmarks, i.e., MMBench and POPE, we noticed a significant improvement in capabilities due to high-quality instruction tuning data, LLAVA SFT+, as shown in the tables. The LLAVA SFT+_, 7B, model demonstrated this with an impressive performance of 52.1% on MMBench and an 82.7% F1 score on POPE, marking an improvement over the original LLAVA by 13.4% and 6.7% respectively. However, it's important to note that LLAVA SFT+, still lags behind models like Cosmos and Shikra. Despite this, LLAVA SFT+, stands out in terms of sample efficiency, using only 280K fine-tuning data, a 5% fraction of what's used by the aforementioned models. This improvement isn't limited to just one model size. When scaled up, LLAVA SFT+_, 13BX336, achieves notable results, reaching 57.5% on MMBench and 82.9% on POPE. In comparison, the effect of RLHF on the capability benchmarks is more varied. LLAVA RLHF shows slight degradations at the 7B scale, but the 13B LLAVA RLHF improves over LLAVA SFT+, by 3% on MMBench. This phenomenon is similar to the alignment tax observed in previous work. However, with our current empirical scaling law of LLAVA RLHF, we believe RLHF alignment would not generally harm the capabilities of LMMs for larger-scale models. RLHF further improves human alignment benchmarks. From another perspective, even though high-quality instruction data shows large gains in capability assessment, it doesn't improve much on human alignment benchmarks including LLAVA bench and MMHAL bench, which is also evident in recent LLM studies. LLAVA RLHF shows a significant improvement in aligning with human values. It achieves scores of 2.05, 7B, and 2.53, 13B, on MMHAL bench and improves LLAVA SFT+ by over 10% on LLAVA bench. We also presented qualitative examples in a table, which shows LLAVA RLHF produces more reliable and helpful outputs. We conducted ablation studies on LLAVA_7B and evaluated it over the four aforementioned benchmarks. In a table, we evaluated the impact of individual instruction tuning datasets. For simplicity, we did not adjust the mixture rate, leaving that consideration for future research. Our findings show that AOKFK significantly contributes to performance improvements, boosting results by plus 9.8% on MM bench and a more modest plus 3.8% on POPE. In contrast, VQAV2 is particularly influential on POPE, where it leads to a 6% improvement, while only having a slight impact on MM bench. This difference can possibly be attributed to the overlapping yes-no format in VQA and the multiple-choice structure of AOKFK. Flickr 30K notably enhances the performance in LLAVA bench and MMHAL bench, likely due to the inherently grounded nature of the task. Furthermore, combining these three datasets results in compounded performance gains across various capability benchmarks. We compared the performance of Factually Augmented RLHF, FACT-RLHF, with standard RLHF in a table. Our findings show that while the conventional RLHF shows improvement on LLAVA bench, it underperforms on MMHAL bench. This can be attributed to the model's tendency, during PPO, to manipulate the naive RLHF reward model by producing lengthier responses rather than ones that are less prone to hallucinations. On the other hand, our FACT-RLHF shows improvements on both LLAVA bench and MMHAL bench. This suggests that FACT-RLHF not only better aligns with human preferences but also effectively minimizes hallucinated outputs. Section summary. The authors used LLAVA bench and MMHAL bench as evaluation metrics, along with MM bench and POPE, to assess the performance of large multimodal models, VLMs, in various benchmarks. They found that high-quality instruction tuning data led to notable improvements in capabilities, with the LLAVA SFT$+ model achieving impressive results. However, it trailed behind other models in terms of overall performance. On the other hand, RLHF showed mixed results, with LLAVA RLHF improving over LLAVA SFT$+ in some benchmarks. High-quality instruction data had limited impact on human alignment benchmarks, but LLAVA RLHF showed significant improvements in aligning with human values. Ablation studies revealed the contributions of different datasets and the effectiveness of FACT-RLHF in minimizing hallucinated outputs. Section. Data filtering versus RLHF. In our initial experiments, we used the FACT-RLHF reward model to eliminate 70%, 50%, and 30% of LLAVA data. We then fine-tuned an LLAVA model using this filtered data, which resulted in scores of 81.2, 81.5, and 81.8 on the LLAVA bench. However, the performance on MMHAL bench, POPE, and MM bench remained largely the same. We think this lack of improvement is due to two reasons: the lack of a mechanism to provide negative feedback to the model when it produces hallucinations, and potential limitations of our FACT-RLHF reward model, especially when compared to more powerful oracle models used in previous studies. Recent advancements in large language models, LLMs, such as GPTs, PaLM, Bloom, Llama, Alpaca, and Vicuña have led to significant improvements in multimodal models. Flamingo was the first to incorporate LLMs into vision language pre-training, using gated cross-attention dense blocks to adapt to visual features. Its open-source versions are OpenFlamingo and IDE FICS. Poly studies the scaling factor of vision and language components across various tasks. POM-E extends LMM to the embodied domain. BLIP2 introduced the querying transformer, Q-former, to bridge the gap between image and language encoders, which was further improved by Instruct BLIP. Otter focuses on enhancing OpenFlamingo's instruction following capability. MINI-GPT-4 suggests that GPT-4's effectiveness is due to sophisticated LLMs and recommends using a single project layer to align visual and linguistic models. It showcases abilities similar to GPT-4 but is more computationally efficient. MPLUG-OWL offers a new approach, initially aligning visual features and then fine-tuning the language model using LoRa. Recently, QuenVL scales the pre-training of LMM to 1.4B data and achieves impressive results across benchmarks. Among them, LLAVA pioneered LMM work by harnessing GPT-4 for generating vision-language tuning datasets similar to text instruction efforts. However, due to the syntactic nature of these generated datasets, misalignments between image and text modalities are prevalent. Our research is the first to address this misalignment through RLHF. Before the advent of LLMs, the NLP community primarily defined hallucination as the generation of nonsensical content or content that deviates from its source. The introduction of versatile LLMs has expanded this definition, as outlined by into 1. Input conflicting hallucination, which veers away from user-given input, exemplified in machine translation. 2. Context conflicting hallucination, where output contradicts prior LLM-generated information. And 3. Fact conflicting hallucination, where content misaligns with established knowledge. Within the LMM realm, object hallucination is well documented, referring to models producing descriptions or captions including objects that don't match or are missing from the target image. We expand on this, encompassing any LMM-generated description unfaithful to image aspects, including relations, attributes, environments, and so on. Consequently, we present MMHAL Bench, aiming to holistically pinpoint and measure hallucinations in LMMs. Hallucination phenomena are observed in both large language models, LLMs, and large multimodal models, LMMs. The potential reasons are twofold. Firstly, a salient factor contributing to this issue is the low quality of instruction tuning data for current LMMs, as they are typically synthesized by more powerful LLMs such as GPT-4. We expect our proposed high-quality vision instruction tuning data and future efforts on manually curating high-quality vision instruction tuning data can alleviate this problem. Secondly, the adoption of behavior cloning training in instruction-tuned LMMs emerges as another fundamental cause. Since the instruction data labelers lack insight into the LMM's visual perception of an image, such training inadvertently conditions LMMs to speculate on uncertain content. To circumvent this pitfall, the implementation of reinforcement learning-based training provides a promising avenue, guiding the model to articulate uncertainties more effectively. Our work demonstrates a pioneering effort in this direction. However, while LLAVA RLHF enhances human alignment, reduces hallucination, and encourages truthfulness and calibration, applying RLHF can inadvertently dampen the performance of small-sized LMMs. Balancing alignment enhancements without compromising the capability of LMM and LLM is still an unresolved challenge. Furthermore, though we've demonstrated the effective use of linear projection in LLAVA with top-tier instruction data, determining an optimal mixture and scaling it to bigger models remains intricate. Our research primarily delves into the fine-tuning phase of VLMs, leaving the issues of misalignment in other modalities and during pre-training yet to be explored. Finally, while MMHAL Bench emphasizes the evaluation of LMMs with an aim to curtail hallucinations, it is noteworthy that short or evasive responses can inadvertently attain high scores on MMHAL Bench. This underlines an intrinsic trade-off between honesty and helpfulness. Consequently, for a more comprehensive assessment of alignment with human preferences, we advocate for the evaluation of prospective LMMs using both MMHAL Bench and LLAVA Bench.